Hello and welcome to our Black Hat Arsenal talk. Today's topic is around firmware analysis, especially firmware analysis with EMBA. EMBA stands for Embedded Analyzer, and it is a fully automated security and vulnerability scanner for firmware of embedded devices. And the best thing on EMBA is it is open source. So after this talk, you can right-click, go ahead to our GitHub website, download EMBA and start analyzing firmware. And with this, you can make the Internet of Things a little bit more secure. My name is Michael Messner, and I'm a penetration tester at Siemens Energy. During my daily business, I perform penetration tests on critical environments and critical systems. This is the area where we are using and developing EMBA on a daily basis. And now I will hand over to Pascal, who will give you a great overview on firmware analysis and EMBA.
Thanks, Mike. My name is Pascal Eckmann and I am a software engineer at Siemens Cybersecurity in Munich. I have experience in security research, especially in the field of firmware and embedded devices. Let's get started. Today, everything is connected and communicates with each other. Let it be your private IoT at home or the operational technology in large factories. Without these devices, our digital everyday life wouldn't be possible. Starting with mobile phones connected to smartwatches, across the traffic light on the way to work in your car that gets its software updates over the internet, or the big companies with their huge range of machine control systems and more critical infrastructure like plants. The more of these devices are present, the higher the attack risk. So it makes sense to deal with the security of these devices. A possible attack vector of these so-called embedded devices is often the firmware and must therefore be analyzed. What is firmware? Firmware is the operating system of these devices. This does not have to be a large system like Ubuntu. It also can be very small and from the vendor itself. Many analysis techniques for Linux are well known. There are many tools, even open source, precisely for this purpose. But it so often happens that we don't know the right tool for our research. There are also some commercial tools out there, but in our experience they are quite expensive and mostly limited to a specific use case. EMBA has no limits, costs no money at all, and gives the best results overall. Why is that? To answer that, we need to look at the process of a manual typical firmware analysis. We now assume that we have a firmware at hand. In most cases, it's a single binary file, so you can run the command strings over the file to find plain text like passwords if you are lucky. In the next step, you use binwalk to extract the file and start searching for the typical configurations with find. Perhaps you will search these files with a regex command for interesting parts. Then you Google something, try to get more information about the firmware. Trust me, you will Google a lot. After hours of research, you might find yourself copying an application from the firmware and loading it into a decompiler like EDA or Gitwa. In summary, one can say you will try everything, maybe lose the structure, start new approaches. It can get messy and takes a lot of time. We don't have time for that. Now we start with the interesting part of this talk. EMBA, in short for Embedded Analyzer. As Mike already told you in the beginning, EMBA is an open source firmware analyzer designed to do the manual labor for us. Each step in the analysis process is carried out automatically. The steps to use this tool are very simple. Get the firmware, start EMBA with the firmware as a parameter, and done. EMBA takes care of the rest. It will be extracted, analyzed, and at the end you get a structured HTML report. Let's walk together through the workflow with EMBA step by step. Before we can use EMBA, we need to get our hands on a firmware. There are a few ways to do this. The easiest way would be to Google the vendor, go to his web page, and download the firmware from there. This is often the case when the devices are not being updated over the internet. Sometimes you already have access to the terminal of an embedded device and can copy the firmware to your machine using one of the known protocols. Another possibility would be to exploit an already known vulnerability and, for example, to gain access to the firmware or to the file system with a command injection on the provided web interface. You can also try desoldering the flash memory from the device's circuit board and extract the contents from it if the previous methods didn't work for you. Another operation would be to access the device to an interface like JTAG or SWD. If nothing of these previous methods has worked for you so far, you also can try to sniff the SPI communication from flash to memory. For a device to boot at all, it needs the firmware in memory, and this is where you can get the data. Hopefully, one of these methods presented worked, and we now have a firmware in front of us and can go to the next step in the EMBA workflow. After starting EMBA with the firmware as a binary blob, EMBA must first extract it for further analysis. The easiest way. Binwalk is the standard solution to extract firmware binaries. After running Binwalk, most times I have a firmware to work with. That was easy, but what would happen if Binwalk fails or the firmware is way too specialized? There is a selection of alternative tools such as FreezeNG. This particular tool one is specialized in extracting firmwares from devices made by AVM, a German manufacturer of routers, and you also can find it on GitHub. We are constantly adding tools like this to EMBA to improve extracting, and all of these tools are also installed with EMBA. There are no add-ons for EMBA that are not included in the full package. Still, everything works like a charm. What would happen if the firmware contained a Debian, an ITSI, or an Android software package? I think it would be very interesting to see what these packages contain, and extracting those can greatly improve the final analysis. In the example, you can see the number of files almost tripled after unpacking a single Debian archive. Let's go through the entire extraction process of EMBA together. The extraction modules run one after the other and they realize what they have in front of them. If it's a file system or a VMware image, then it will be mounted and copied. If the image is encrypted, it will be decrypted if the key was leaked, and then Binwalk will extract it. Then there are special binaries like UB or these from AVM. EMBA will select the corresponding custom tool to extract them. All other systems are, if possible, extracted with Binwalk. In the next step, EMBA scans the extracted files for a Linux root file system, and if the result is positive, then it initiates EMBA's main analysis. If not, then the extractor by the firmware analysis and comparison tool will be executed. If after this extraction is still no root file system, EMBA will try to re-extract the firmware. EMBA's deep extractor will find and extract files, systems or binaries within an extracted firmware. EMBA's goal is to fully extract the firmware to the very end, and that's what sets it apart from all competing extractors. That improves the result, and if it succeeds, then EMBA will start the main analysis. Even if the extraction was unsuccessful, for example, if the firmware simply does not have a Linux root file system, EMBA would now start the main analysis. And here we are in the next step. EMBA will now march through a large collection of different analysis modules. All the tools combined with the freshly extracted firmware allows us to do a deep analysis and answer any questions we have about the firmware. Which files are there? Which architectures? Which versions? Which parts from the vendor? Which kernel? Which issues are in the scripts? And much more. EMBA will answer your questions. How does EMBA do that? We don't want to reinvent the wheel. In EMBA we use many open source tools provided from our community to get the best result at the end. Why develop something new when it's already done and out there? Once installed or the Docker container pulled, you have a complete firmware analysis with just one command. Starting with the extractors we are already familiar with, to checksec, CVE search, with a complete databases of all CVE entries, even create classics such as Gitra combined with object dump, QEMU and many more, enable EMBA to present a deep analysis of the firmware. You don't have to get all the tools manually and try to figure out how to use them and waste a lot of time. You can now simply use EMBA. At this point, I hand the floor to Mike, who will now tell you more about finding vulnerabilities using EMBA.
Thank you, Pascal, for a great overview of EMBA and firmware analysis at all. So now let's move on to a little bit of a different topic, the zero-day identification. For this, for me as a penetration tester, it is quite important that I have as much time as possible for the identification of new vulnerabilities. So I need to get an overview of the interesting areas within a firmware. But what are 0 days at all? 0 days are currently unknown vulnerabilities. This means that there are no security updates or patches available. For me as a penetration tester, it is very important that I have to find these vulnerabilities by myself. I can use my own scripts, my own fuzzer, my own techniques, my own brain. At the end, and this is more or less the goal of every penetration test, is to find more currently unknown vulnerabilities and to automate all of the stuff that is possible to automate. EMBA helps you in the identification of such interesting areas with different metrics. The main metric is the identification of legacy C functions. The legacy C functions by itself are not a vulnerability. They are more something like a violation of a secure software development lifecycle. But the more often such legacy C functions are used, the higher is the possibility that something goes wrong. And so you need to count these legacy C functions or the usage of these functions per binary. For this, you can use different techniques. The easiest one, for example, is to use readelf. Readelf on every binary of the firmware, and you know which binary is using such legacy functions. But then you do not know how many times such functions are used per binary. And so EMBA creates a disassembly of every binary and library from a firmware. It uses primarily object dump, which is very fast and reliable. And if object dump is failing, EMBA is using automatically Radare 2. This means that you as a user do not really realize that EMBA is switching to Radare. It is just moving on in the background. At the end, we have a complete disassembly of every binary and library, and we can count the usage of such legacy functions like string copy. And as we already have this disassembly, we can move on with further analysis. For example, we can do a check if there is a string length function used right before a string copy. This means that the string copy is probably not that critical, or at least I want to spend my initial time on another area of the binary. And as we already have this disassembly, we can move on with further analysis. For example, we can check the binaries if they are using functions for network functionality. We can also analyze the binaries, for example, if there are binary protections in place. So an exploitation process would be much harder. And finally, EMBA includes a list of common known Linux files. It is a huge list. And with this list, EMBA can do a guess if this is a common known Linux file, which is probably an established open source project, and you want to spend too much time on it, or if this binary is from the vendor. So no common known Linux file with a lot of string copies or some other functions. So probably you will take a deeper look at this. Let's have an example. I challenge EMBA from time to time with publicly released advisories like this. This is the final report or the output of a firmware analysis from a firmware that includes the famous NCC binary. Such firmwares were heavily exploited by Darkanium. You can read on the advisory in the link on the slide. And you can see after an analysis from EMBA that the NCC binary screams for further analysis. It includes more than 600 usages of the string copy function. EMBA rates it as a non-known Linux file. There are no binary protections in place, and the binary includes network functionality. So probably this would be the first binary that I will load into EDA or Ghidra and take a deeper look at it. Another example is an advisory that was released in March this year by Stereotype 32. It is around Netgear routers. And Stereotype has exploited multiple vulnerabilities in the setup CGI binary. So again, I challenged EMBA with this, and EMBA pointed me directly to the setup CGI binary with more than 1,500 usages of string copy. It is also rated as a non-common Linux file, so probably a vendor file. There are no binary protections enabled, and as an additional metric, also more than 200 times it is the call to system is used. So with this information, we are now ready to go to dig deeper, to take a deeper look at this firmware or at these binaries. So we know where to start. And in the meantime, we can do more automated tests regarding one-day vulnerabilities. So what is a one-day vulnerability? Compared to a 0 day is something completely different. A 0 day, as we have heard before, you need to find by yourself. A one-day vulnerability was already found, and in theory there are patches or remediations available. So at the end, this means that you need to identify the different software components within the firmware. But not just the components by itself. You also need to identify the software version, the exact software version. You need to create something that is called a software bill of material. And you need to do this on a binary level. And in an ideal world, from my perspective as a penetration tester, this should be done completely automatically. So, what is the problem with the software bill of material? So, as mentioned before, we are working on a binary level, on a packed firmware, binary firmware. So, we do not have a software repository with source code available. So, we can just query the software repository and we know which versions are used within our firmware. Additionally, the different software components have different software version strings. So at the end, every version string looks a little bit different. So you need to have a quite huge database in the background, which includes all of these different software version strings. And additionally, there is no standardized mechanism or parameter available to query this version information. So let's have a short look. For example, if you check out bash on your Linux system, for example, you can query the version of bash with -- version, and then you get something back like bash, GNU bash, version something. You as a human, it's no problem for you as a human to identify this as a version identifier. But EMBA, we will see it a little bit later. So on another software component, apt, you do apt -v, and then you get apt and the version number. On OpenSSL, you query the version number with the parameter version, no minus and no minus. Then you get OpenSSL 111 and then a letter, so in this case K. Interesting is also the version identifier of Perl, -V, and then you get summary of Perl 5, revision, version, subversion, and so on. And you can see that all of these versions are looking different, and you need to query different version parameters for the extraction of these details. So at the end, EMBA includes different possibilities to identify such versions. Most of the firmware analyzers that I know of are using just static analysis mechanisms. EMBA uses this also, so output generation with, for example, the string command, or you analyze the kernel modules, which include the kernel version that they need, or sometimes you will find version details in the path of a binary or in the name of a binary or library. Additionally, EMBA tries to emulate every binary from the firmware and generates output via this emulation process. And at the end, it doesn't matter if static or dynamic analysis. At the end, EMBA matches the results or the output that is generated against a version database with different version identifiers. And you will get results like this. You can see there are different version identifiers, like from BusyBox version 1.12.1, DNS mask, IGMP proxy, IP tables, and so on and so on. All of these version identifiers are looking different. So it's not that easy to query further databases with these version identifiers. At the end, you need to normalize these identifiers for further processing. So now you can see the output of this normalization process. With this version information, we are now able to query, for example, the CVE database. And at the end, we know the binary name, we know the version that we identified. From the CVE database, we got back the CVE number, and with this CVE number, we can now query multiple other databases, like the exploit database, to get current proof of concept and exploit codes. In this exploit database, we also get details about is the exploit a denial of service exploit, the remote exploit, the local exploit. Additionally, we can query, for example, the Metasploit database. Same like before, we get the information if it's a denial of service or remote or a local exploit. And we can query other databases like the Routersploit database. Or we can query collections of proof of concept codes and write-ups regarding all of these exploits on GitHub. At the end, we will have a very nice and shiny final report with an overview of the identified versions or the software components, the versions, the CVEs that we have identified, and the exploits. In this case, we were able to identify 29 different software components. In these 29 software components, we have identified more than 1,700 CVEs, so known vulnerabilities, with 400 high-rated vulnerabilities. 23 different Metasploit modules are available. So these are typically the exploits or the modules that you will try first because they are most tested, they are most stable. And another quite interesting information or piece of information for you as a penetration tester, but also for you as a security team. There are 9 remote exploits available. These are the exploits that you want to take a first look at it. So now we are nearly done with our EMBA workflow. With this structured workflow, we were able to extract the firmware from the binary. So we got something like a root file system. If it's a Linux file system, we got it out of the binary. After these extraction modules, we have analyzed the firmware regarding configuration issues. We have analyzed it regarding outdated software components and vulnerabilities and exploits. And we also identified spots or areas within the firmware that we probably want to take a deeper look. The next step are the EMBA Live Tester modules. These are currently under heavy rework, so we will see a little bit more around these modules in a few weeks. Finally, there's the EMBA Final Aggregator. The aggregator takes the pieces from all of the different modules, puts them together into the report. And so at the end, you get something like the final overview of all of the known vulnerabilities. And now it's time for a quick demonstration of EMBA and a typically firmware analysis process. So now let's proceed with a live demonstration of EMBA. I will demonstrate you EMBA probably in the same way you will learn to know EMBA a little bit more in detail. So first things first, we have already downloaded the firmware that we're going to analyze with EMBA. Then, where can we get EMBA? So just go to the GitHub site of EMBA and you will find the source code. Some other interesting things, you will find the wiki, which will give you a lot of background information around the features of EMBA, around the installation and the usage. But the main page probably will give you everything that you need for your first startup. So let's scroll down a little bit and you are directly in the installation instruction. And this installation is quite easy. You can git clone EMBA. Let's go to this directory. So we can clone EMBA. After a few minutes, we have the whole EMBA directory locally, and we can see it over there. You can see different binaries and directories. Probably the most important thing for you is the EMBA script by itself and the installation script. Now we will check out the installation script. So the installer will help you a little bit in what are you typically doing with it. So EMBA supports multiple installation modes. The main installation mode or the default installation mode is -D. This means that EMBA will download a complete Docker container for you with all the tools that EMBA will need pre-installed. So this is the most used EMBA installation mechanism. On the host, only the CVE database is installed for centrally management. You can also install everything on your host, but be prepared, it will take a long time and it's also a little bit error prone. So now let's give it a try with the default installation mode. So you can see the package list is updated, everything is the Docker container will get downloaded and the CVE database is downloaded and populated and set it up everything. So at the end we will have something, some Docker image, which is called Embedded Analyzer EMBA, and this Docker image is the thing that will analyze your firmware. Within this Docker image, you have installed all of the tools like mentioned before. So as I stop the installation, I have already installed everything in another subdirectory, so to make it a little bit shorter. And now we can take a look at EMBA by itself. So just execute EMBA. And you can see there are different options available. For example, you can predefine the architecture of the firmware. Very important is the log path to the log directory where EMBA writes all the log files. The firmware path for sure, and you can use some other options, like you can just execute some special modules, you can enable some special features like the CVE checker. Also the web reporter. So EMBA will write the final HTML report that you can just analyze or do just some further analysis in your web browser. You need to activate it manually. What else is probably interesting? Yeah, for sure. Multi-threading to speed up things. So EMBA automatically detects how many cores do you have in your machine, and it tries to use these cores as effective as possible, so to speed up the whole firmware analysis process. So let's give it a first try to start up EMBA. As mentioned before, we have the firmware already downloaded. We will write the log files to this directory, and we are using a scan profile. As we have seen before, EMBA supports a lot of different possibilities to tweak the scan. In the default scan profile, most of the really useful options are already set, like output coloring, like enable the HTML report, or enable threading. So let's give it a try. What you can see here, first of all, these are the settings that EMBA activates via the profile, and then EMBA is doing a basic health check, this time on the host. So EMBA doesn't need a lot of things on the host. It needs the Docker container, the Docker environment, and the CVE database. It also checks if the directory is already available and asks you for confirmation to overwrite this directory. So let's do it. And now EMBA starts up the Docker container, and you can see the health check is massive now. All of the tools that EMBA is using during this analysis task are now tested. For example, also binwalk, Radare, root exploit database, FreeZNG, and all of these different things that are already available in the Docker container, and you do not need to install it manually, are checked. And then the pre-checking phase is starting up, which means that EMBA is doing a quick analysis of the firmware file and tries to extract these firmware files. You can see some details on the firmware file, and you can see that it already identified a zip file, extracts the zip file. You can see the firmware bin now over there, and then it starts up with further extraction with the deep extraction mode, and you can see the typical binwalk output now. It identifies a squashfs file system, extracts the squashfs file system, identifies the root directory within this extracted binaries, and proceed further with architecture detection. And then it starts up the testing phase. And the testing phase are more or less the analyzers that we have already seen in the slides. So now EMBA is trying to analyze all of the things within the firmware. So configurations, binaries, and so on and so on. Give me a second. I will show you another interesting thing. So as mentioned before, EMBA is threaded. So EMBA takes all of your cores as effective as possible. And so you can see that all of your cores are currently working. With this, we're going to stop this analysis, and we open now the final HTML report. So this is the dashboard of this HTML report. You can see the main details, for example, which kernel was identified. And all of the information, all of the output from the modules is linked together now. So you can just click on this information and you're in the output of the module. For example, you can see the kernel, the identified kernel, the output of the Linux exploit suggester, for example. So for identifying interesting exploits. Scroll down a little bit. you can see the details on the binary level. So the already mentioned NCC binary. The output is also, or the details are also linked now. You can just click on this. You can see the binary protection output over there and all of the identified string copies for your first teardown. And finally, the things that we are already mentioned in the one-day detection, software inventory. You can see every software component with the version details and the identified CVEs and exploits. For example, now you can click on the mini UPnP daemon. You will find 5 CVEs and 2 different exploits for these CVEs. You can click on this exploit database details to get directly to the further details over there. Or regarding GitHub, we also try to identify exploit code, proof of concept code or write-ups on GitHub. And we can click on this and we directly go to this GitHub repository. And here we can find some write-up and some proof of concept code now. So we can move through the whole report now. Here you can see the final information regarding how many Metasploit modules, how many remote exploits. So that's it from my side, from my perspective. This was a short demonstration on EMBA. I hope you're interested, and now you can download EMBA from the GitHub site and go ahead with it. So finally, we are at the end of our talk. So the last great thing that we have for you today is the release of the new version 1.0, which we have released this week after 1.5 years of public development. So go to our GitHub site, check it out and scan all the firmwares with EMBA. Thank you and have a good time.